Welcome to General Chemistry Mini Lecture Series, Lecture 31, Formation Reactions. Formation reactions have to occur under standard conditions, or standard states. Here are the standard states. The pressure for pure gas is 1 atmosphere. For pure liquid or solid, the pressure is 1 atmosphere, and the temperature normally 25 degrees Celsius. For solutions, the concentration must be 1 molar. Delta H0, that means the standard enthalpy change, and that is actually the enthalpy change when all reactants and products are in their standard states, like what we just talked about here. Standard enthalpy of formation, we use delta H0F to represent the standard enthalpy of formation. That is actually the enthalpy change for reaction forming 1 mole of a pure compound from its constituent elements. Please note the elements must be in their standard states. For pure element in its standard state, the delta HF0 is always 0 kilojoules per mole. That's by definition. Now let's address a formation reaction. Those are the reactions of elements in their standard state. We already talked about the standard state. To form 1 mole of a pure compound, the coefficient of this pure compound must be always 1. For example, carbon reacting with oxygen, forming carbon dioxide. The coefficient for the compound in question has to be 1, in this case CO2. But in some other cases, it may be fractions, like in this one. Look at this reaction. The coefficient for the pure compound needs to be 1. Then we need to have a fraction before oxygen so that this equation can be balanced. 3 oxygen on the right-hand side, and now 3 oxygen on the left-hand side. So therefore, in this case, fractions are allowed, even though in general, when you balance a chemical reaction, fractions are not allowed. Here they are. Elements at their standard states, the delta H0F has to be 0. And here is just a table of selected standard enthalpy of formation values. Hydrogen atom is not the most stable elemental state for hydrogen. Hydrogen molecule in gas state is. Let's take a look at carbon. Graphite is the most stable state, not diamond. And we have many other examples. Therefore, when you write formation reactions, make sure the elements has to be in the most stable form. If you take a closer look at this table, you can see some other diatomic molecules behave the same way as hydrogen does. For nitrogen, the most stable state is gases N2, and for oxygen, it's gases O2, fluorine gases F2, chlorine gases Cl2. But for bromine, it is Br2 in the liquid state. That's the most stable state. Iodine is a I2, the solid state. For most metals, the most stable state is the solid state. They should have a delta HF0 of 0 kilojoules per mole. Let's work on one example. We want to write the formation reaction for carbon monoxide. Okay, so first we know the reaction has to be involved carbon and oxygen, and the product has to be CO. And we have to follow those rules we just talked about in previous slides. We have to use the more stable states for each element involved in the reaction. Carbon, the most stable one, is clarified state. Oxygen has to be O2G. And next, we have to take care of the coefficients. Okay, since in formation reaction, the coefficient for the pure compound, the only product in such reactions, has to be 1. The coefficient for O2 has to be a fraction, which is 1/2. Let's work on the second example. We want to write the formation reactions for the following compound. Ammonia has to be from nitrogen and hydrogen, and both we need to use diatomic and has to be in the gaseous phase. Coefficient for ammonia has to be 1. Because of that coefficient of 1 for ammonia, we have to use fractions to balance N and H so that this formation reaction is balanced. CO2, we already talked about it. Iron 3 oxide, again, the coefficient for the product or for the pure compound has to be 1. Then we need to use 3/2 to balance O2 so that this formation reaction is balanced. Methane. Carbon has to be the most stable state, or the standard state is clarified. Again, hydrogen should be diatomic molecule in the gaseous form, and then you balance this equation. Now we are going to address the enthalpies of reaction from standard enthalpy of formation. We can use this equation to calculate the enthalpy of reaction. The first term here is the enthalpy of formation values for the products, and the second term is for the reactants. And the N means the coefficient of each product or each reactant. I'm going to show you that in more details using this example. We need to calculate the enthalpy change in this reaction. We will use this equation here. Let's first work on the products. For CO2, that's why the N for CO2 is 4. 2 water molecules, the N for water should be 2. And do the same for the reactants. Next, you just simply plug in those delta H0F values, and those will be given, or you can find them from a table of enthalpy of reactions. Start with the CO2 first. 4 times CO2's standard enthalpy of reaction value. Make sure you have to include the sign, and then 2 times water's, so those are the products. And now do the same for the reactants. For oxygen, the standard enthalpy of formation is 0, okay, because that's the most stable state of element oxygen. Now the answer is negative 2600.4 kilojoules. Here are the end of lecture 31 quiz questions. I will see you guys in lecture 32.